All right. Good afternoon, everyone. We're going to be discussing the IEEE-Compatible UVM reference implementation. This is going to be a deep dive into what's coming with that reference implementation. My name is Justin Refice. I'm from NVIDIA. I'm the chairman of the UVM Working Group in Accellera. I'm going to be joined today by Mark Strickland from Cisco, vice chair of the UVM Working Group, Mark Peryer from Mentor, a Siemens business, Simm from Cadence, and Srivatsa Vasudevan from Synopsys. And we're each going to be going into specific sections of the standard of the changes that are done. Now, my specialty when it comes to the UVM Working Group is the agenda. That's really what I'm going to be hammering on. Right? So Mark is going to start the day with an introduction, a what and why to what's going on in the reference implementation in 1800.2 and 1.2, and some useful information for new users and for people migrating from 1.2 and from pre-1.2. He will then hand the ball off to Mark from Mentor, who will cover changes in UVM object and the policy classes, which are both old and new at the same time. He will then hand the ball over to Uwe. Uwe will cover deferred initialization and the changes to UVM RAL and UVM regs that have occurred. And then he will hand the ball off to Sri, who will cover changes in the configuration space, callbacks, reporting, and a very brief discussion of some things that have changed in sequences. At which point then it will come back to my excellent handling of the agenda, wherein we'll discuss the future. The Accellera UVM Working Group, as I said before, we are the working group responsible for the reference implementation of the 1800.2 standard. We are one of many working groups inside of Accellera working on verification challenges. UVM's one, System C is another, UVM System C, UVM multi-language is yet another. And we are a group of volunteers where we're all effectively users of the standard. Everybody on the committee uses the standard, either from a tool provider, VIP vendor, or an end user. I mean, we've got the whole gambit is covered. And our responsibilities have changed a little bit. Mark is going to go into this in some detail. The UVM Working Group in Accellera used to handle all things UVM when it came to standardization, examples, and all of that. Now that the IEEE has officially released 1800.2, they own the standard. So it's more of a dance between the two committees now and who's doing what and when. And as I said, the UVM Working Group right now is primarily focused on the reference implementation. In the future, that will change. But that is going to be the main driving force for our committee for 2018 and going forward. So at this point, I would like to hand the ball over to Mark, and he can discuss what we're here for.
Thank you, Justin. Yeah, so I am Mark Strickland from Cisco. I've been on the UVM committee for a number of years and the IEEE committee as well. So hopefully I can take you through some of the changes. This may be a review slide, but it's just a quick reintroduction. 1800.2 was the IEEE taking up UVM and making it an IEEE standard. And the main thing that we want to get across to you now is that the Accellera UVM committee is focused on doing just the library. So no longer are we working on the standard and the user's guide examples. We're passing all that off to either the IEEE or the third parties. But what we're going to be delivering to you now is the library itself. I also wanted to note that an implementation of the standard can do more than what the standard says. There's nothing that the standard doesn't say this is the complete set of what you can do. It just says this is what you must do. So we're also going to get into what are some of the extra things we do and how do we help the user deal with that. IEEE came out with 1800.2. It was published last year, I believe April or May of last year. And since then, the Accellera committee has been tasked with coming up with a library to match that. So we had to first decide how we were going to do that. And these are the steps that we came up with. The first thing we want to do is start with the existing library the 1800.2 standard was based on a lot of the concepts that were in our UVM 1.2 library. So why throw out a lot of the good there? And also, if we start with the 1.2 library, we're less likely to break people who have been using 1.2. So it seemed like a good starting point. But the first thing we decided to do to make things easier for changing was to remove all the code that was already under deprecation in 1.2. So 1.2 had switches in it that would allow you to use things that used to be in 1.1 but were no longer in 1.2. All of that code we got out of the library. We'll get to what that means, but if you were using 1.1, the first thing we want you to do is to get to the point you can use 1.2. After we removed all the old deprecated code, we then have to add in the new API that 1800.2 has recommended. And having added that API, just to make things consistent, we want the library to also use that API. So the changes involved would be adding things that were not in there anymore and finding out where the old 1.2 code called things that have now been replaced and have them use the new API. Next, there's some API, it's not many, but there's a few, that were actually in 1.2, documented in 1.2, but now they're in 1800.2 documented in a different way. Perhaps the signature changed, perhaps some of the semantics changed. We had to go ahead and make those changes as well. And then for anything, after we've added all this API, if there's any 1.2 API that still exists that is really doing the same functionality, it was really intended to be accomplished by the new 1800.2 API, we're going to deprecate that API. We don't want to have a library that gives you multiple different ways to do the exact same thing. And the 1800.2 API, the intent was to give you a better way to access things. So we are moving towards that, and the old API will be put under deprecation. And finally, as we were doing this work, we didn't restrict ourselves to doing just 1800.2 work. If there were some existing bugs reported against 1.2 and they were fairly simple to fix, because we're getting out of release, we tried to take care of those. So you'll find some bug fixes as well. All right, so having done that, what did we end up with in the 1800.2 library? So what you're going to find is there's some new API that gives some new functionality to users. These could have been things that you really couldn't do in 1.2. Some things are new and cool, and they'll be described today by the speakers after me. Some of the things in here maybe you could have done, but you had to be pretty sneaky to do it. So I know that there's creative users out there that were going well beyond the documentation of 1.2 and looking to the source code and saying, "Ooh, there's cool stuff here I could use." That we want to put a little damper on. We don't want people doing that too much. So 1800.2 tries to document a way to do all those things, and now there's new published API that's going to let you do that. Also, in the library, you're going to find some alternate API that gives you ways to do things that you were already doing. And you were using documented 1.2 API. Now there's a different way to do it in 1800.2. So the new library will give you a way to do this in a cleaner manner, and it will also give you the possibility of using deprecated mode for a while. And then there's a few 1.2, and I really want to emphasize the word few. There's really not many. There's a good chance that many users will not encounter any of these. They're probably not in the mainstream that everyone's going to encounter it. But there are a few that are incompatible with 1800.2, and those are going to be unavailable. So there will be some user code changes that will be required for anybody using these types of things. I mentioned this before, but we're going to have a superset of the 1800.2 API. I just want to get that clear in everybody's minds. So the final library we've got has all the 1800.2 API. It's also going to have some additional API that Accellera has added. If anybody else comes along and implements an 1800.2 library, they may or may not have this API. They may have extra API that we don't have. But the library itself is 1800.2 plus these additional things. The things that we can picture are going to be in there are certainly we're going to have some API that we're using internally that we don't intend to be used by the public. These are things that won't be documented, and I would personally encourage you not to use those things, not to dig into the code and try and use those, because they are things that the library makers feel are free to be changed in the future. If we're doing an implementation, we don't need to worry about any compatibility for anything that's undocumented. But there will be some things that we do expect the users to use. we're going to put things that are debug aids in. So there were a number of things in UVM 1.2 that were in this category. Some of the command line interface code would give you ways to get more messages out when you were doing things like resource DB accesses. Those types of things are still in our library, and they're going to be in our domain as the Accellera library, and we will be documenting them. They're not documented in 1800.2. Another category is that we might include some API that we think is very useful for users, but was not included in 1800.2. And these would be extra things that we would intend to contribute back to the 1800.2 process in hopes of getting them in a future version. So there may be some API that we document for a while, and then it gets taken up by a future version of 1800.2, and we no longer document it. It's just part of the standard. I don't think there's that much in that category right now because we're really coming off a place where we originally contributed the information to IEEE. So most of what we already had in 1.2 is in the IEEE standard. And then the final component is going to be this one I've alluded to, the deprecated set, where there's some API that is only available when you set a define, and it will all be non-conflicting. It just becomes an additional API that you can use in order to maintain your existing user code for a while until you're able to make any changes to update to 1800.2. All right, so talk a little bit more about the deprecated code. The idea is that a lot of what went into 1800.2 was giving you alternate and cleaner API for doing things that you're already doing. So really wasn't intent for this new API to be replacing other API. This API that was getting replaced, we realized people might not be able to replace it immediately. So we are going to put that into a section of the code that is only compiled in if you include this define I show here, the UVM-enabled deprecated API. The code that can go into this category must be non-conflicting. So the idea is that you can set this define. It will include extra code. This extra code will then tie into the normal API. It will just give you an additional way to get into the standard API using the old style. If you can get to the point that you do not use this define, then you can compile your code and see that, in fact, you're using nothing but the 1800.2 API, because if you use any old 1.2 API, your compile will fail. The API will not be in there unless you use the define. And by default, we're not going to put the define on there. So the anticipated process is that users might set this for a while, eventually fix up their code, remove this define, and be able to see that they are fully using the supported 1800.2 and not the old 1.2 API. Now, having said that, we have seen that there's a small number of situations, and again, I'll emphasize small. It hasn't been many cases of this, but we have seen that there's possibilities that things could not be put into deprecation because it just conflicted with what 1800.2 said. So an example of this is the UVM packer. A couple of things within the UVM packer. One is that in 1.2 there used to be attributes you could put on the fields to say whether they were physical fields or abstract fields. Now in 1800.2 there's a different way to accomplish this functionality, and there's no way that we could say include these fields and also have it feed into the API cleanly. So unfortunately these ones did not make it in, and if you've got physical and abstract and you're making use of it in your UVM packer, you will have to make some modifications to the code. Another one is the use metadata. So that was a flag in the packer to say there's some additional information that the packing and unpacking routines can use to understand how big arrays are, etc. That is, again, in 1800.2 accomplished by the UVM policy classes and what you do with those. Again, we looked at trying to keep this in and allowing people to continue to use this, but we found it was just fundamentally incompatible between how the pack and unpack of objects work versus the packing and unpacking of strings. And so we could not add it in deprecation. So from the Accellera committee, I just want to tell everyone we've tried to put as much into deprecation as possible to ease your transition into using 1800.2, but if it's not in there, there's probably a good reason it was incompatible. The other thing I want to say about the deprecation is that no matter how you set the flag, our golden rule is that we're always going to support 1800.2. So if you set the flag, you're just getting some extra API, but you're not going to be breaking anything that you could do if you were just using what the standard tells you can do. If you look at the graphics here, we see that if you're using the flag, you get the 1800.2 API, you get our additional debug API, and any future API, anything we're intending to contribute back to 1800.2, plus you get this deprecated API. If you don't use the flag, you get all the same picture, you just don't get the deprecated API anymore. So if you tried to compile your user code that was trying to pull any of the old 1.2 API, you did not set the flag, you're going to get a compile failure because it's not going to be there. All right, how about documentation then? So we've mentioned that there's some code that we are keeping from 1.2. There's code that we are implementing based on what 800.2 says. How is all the documentation going to work here? Our golden rule here is that we don't want to be duplicating any information. So we end up splitting the documentation some. What Accellera is going to provide is HTML documentation, much like you had for UVM 1.2 before, but it's only going to contain a small set of what's in the library. It will contain information on that extra API that was intended to be used by the end user. So all the debug API I mentioned, we will put the documentation for that in HTML. And anything that describes additional information about how you use 1800.2 API that was not in the standard, we will also put that into our documentation. The end result is that we're expecting that the full set of documentation you would have for using our library with 1800.2 would be the standard itself, which would describe the basic idea behind the API, and then our documentation, which could provide additional information about what happens when you use that API, and our documentation that describes new API that was not in the standard that was intended for debug use or some other reason that it was intended for end use by the user. So if we look at the graphic on the bottom, the 800.2 API, if you want to find out about that, you want to go look at the IEEE standard itself. We're not going to duplicate that information, possibly get it wrong, and have conflicting information. No, you just go look straight at the standard. If you want to look at the debug API and future API, that's the kind of stuff we're going to have in our HTML. If you want to find information about the deprecated API, then you have to go back to 1.2, where we're not really trying to document how to do deprecated things. We're assuming that the only reason you've got those is because they're in user code that's already working, right? So your intent is just to keep it working until you're able to migrate forward. All right, another question you might have is, does my user code rely on this extra API? So the reason you might have this is because IEEE is now a standard, it's possible that there could be other implementations that are based off the standard. And if you are using API that we are providing that some other implementation of the standard does not provide, then you won't be able to migrate it very easily. And maybe that's an issue for you. Probably not initially, but down the road it could be. So the answer from Accellera is that we're not providing any compliance check. That would be some extra work that we are not signing up for, at least right now, to help you understand if you're using the extra API or not. However, there are a couple of techniques that will get you some of the way. The first thing is that if the reason that you've got some use of extra API is because you're bringing code over from 1.2, one of the first things you can do to knock out a lot of the issues is just try compiling without the deprecated flag. And then at least you're going to see any indications of using that old API that no longer exists in 800.2. And the second thing we're doing to help out is that we are putting tags in the library and the actual System Verilog source code that are by every class and function that are in the standard, so that a linter, which we are not providing, but linters could pick this up and use this to understand, oh, this is API that is coming from the Accellera implementation of IEEE, and it is official IEEE documented. So that's the graphic you see here on the bottom above the description of the UVM object class. We've got this comment here that's got information about UVM 1800.2, what version of the 1800.2 standard we used, and 531 is the section number where you'll find this. So that information will be in there. It is conceivably useful for determining whether you're using the API, but again, we're not providing that final tool to determine that. We're just giving you the information that it could use, the tool could use to do that. That gets us down to what are the steps we're recommending to everyone to update. So the first thing that you need to do is make sure that your code can run with UVM 1.2. So I mentioned as part of our process, we got rid of all the deprecated code that was already in the 1.2 library. So in order to make the jump to this library, you will have to be running against 1.2 and make sure that you have not defined that UVM no deprecated. That was the flag that used to exist in 1.2. This tutorial doesn't talk about how to do that. There have been previous tutorials, I guess, on how to do that and other information on migrating to 1.2, but that needs to be the first step. Okay, once you're running against 1.2, the next thing is to try and take that user code and run it against the 1800.2 2017 library. And you can try that with the UVM enable deprecated API just to minimize the number of issues that you're going to see initially. Once you've set that define flag, any compile failures you see are going to be the result of incompatible APIs, or heaven forbid you are digging in and using undocumented 1.2 features. Any of that would need to be cleaned up. Then the third step would be move forward and don't set the deprecated define, and then clean up the compile failures that you would see then. And those are going to be the result of deprecated APIs, and they will generally have a fairly easy migration path to the 1800.2 equivalent. Oh, and linting tools can help you as well. So how are we going to release this library? The first thing we're going to put out is an early adopters release, and then we're going to follow that up with the full 1800.2 release. The difference between them is really the documentation. So I mentioned we're going to have that HTML documenting additional features. That just took a bit more time, and we didn't want to hold up getting out a release that supported people that were writing code for 1800.2. So that's why the early adopters release is here. We focused our attention on getting the changes to the library. That will all be in the early adopters release. And then we're going to get that out, get some comments on it, maybe have to fix up some things based on the comments. Plus we'll be working on the documentation, and we will then get the documentation out, say maybe 6 months afterwards, something like that.
Just to introduce myself, I'm from Mentor, a Siemens company. I've been involved with UVM all the way through from OVM through UVM up to the present day, but tended to work in the background, working with colleagues from Mentor who are actually directly contributing into the working group. In those days, I think each company had one person that was allowed to use the Git repo. Now, things have expanded somewhat, so there's lots of people making all sorts of contributions. Right, so today I'm going to really just talk about two subjects, and it's really to sort of peel away to the next layer of detail about some of the changes that have been made, and also to try and sort of lift things a bit and actually make it a bit more obvious why some of the changes have been made. So the first thing to say is that UVM object, which is the kind of, sort of core class of the whole UVM library, has had relatively few changes, but actually there is one which interacts with policies and configuration which is worth knowing about. So the first thing to say, and this is sort of right down in the detail of how random seeds work, is that in UVM 1.2 there were a couple of methods that were added into the UVM object which actually allowed you to interact with how seeding was set. the names of those functions have now been changed. So there is a get and set UVM seeding, which is interacting with the core services part of the library. And those are just more logical names for the UVM 1.2 version of the same calls. So that's one of the things which will show up on the deprecation. So the next thing which I'm going to talk about is there's a couple of new methods that impact configuration and policy interactions. So interactions with the UVM policy classes like UVM printer, comparer, and so on. So there is a new method which is called doExecuteOp. And what that takes is a new class that's called UVM field op. And I'll be discussing this in a lot more gory detail. The other method is setLocal, which is really aimed at trying to rationalize all of the different approaches to being able to set different types in the config database. And Sri will be talking about that towards the end of this overall tutorial. So doExecuteOp. This is a new callback which has been added to allow greater flexibility in what we might term field operations. So the idea here is that this configuration, it works in conjunction with policy objects. And it takes this new class, UVM field op, as its argument. So UVM field op basically contains a UVM policy object, a field flag, which basically says this is what this operation is supposed to be doing. So there are some built-in flags which cover the normal field operations such as copy, compare, print, record, pack, unpack, and set, which is to do with configuration. Something else you can do is also define your own fields. So you could define your own field flag for a specific field operation if you wanted to do that. So this is a new kind of area of extensibility that's coming to the library. And then there's a third member of this class, which is the right-hand side. It's the thing that you're going to operate on. And that's used in things like compare, copy, and set operations. So in other operations, that will tend to default to null, as you've seen in earlier versions of the library. So when it comes to configuration, configuration works as it did. You can use field macros to allocate where a particular field inside an object, which methods it would get added to. Or if you don't use field macros and you use alternative approaches like using the UVM config DB, that will still work. Or you might even have other approaches, maybe using direct assignments and so on. So all of that will still work as before. However, when we get into using the doExecuteOp method, what will happen is in 1800.2, the field macros will actually implement code so that it will be executed during the doExecuteOp callback. So if you're using field macros, then you'll need to be careful about exactly what you do and which type of field operations you use with it, because there could be an overlap between the two. Otherwise, you can implement any configuration scheme you like using doExecuteOp. The next thing to talk about is policy classes, and I'll explain how the policy classes interact with the doExecuteOp method. So there are some changes in the way in which the UVM policies are structured between 1800.2 and UVM 1.2. And there are a few kinds of overall use model changes which are really kind of in addition to rather than subtraction from. And what I'll do is take you through some example applications of these changes. So the first thing is that all of the field operations now have a policy. So this basically means that there is now a policy object called the UVM copier. So this is new. And the other thing which is different, which shouldn't affect any user implementation, is that all of the policy classes now extend from a common base class, which is the UVM policy class. And that policy class has base functionality in it which is shared. And the things which are shared are the ability to be able to flush the state of the policy. So if you have a policy which is by definition kind of storing some state as it's processing different objects, then you can flush it at the beginning or at the end of the policy processing. It's possible now to these policies to add some extensions. And I'll talk about that in more detail in a moment. But the idea is that there is a handle within the policy object to a queue of extension objects which could be potentially used to customize policies. It also keeps a stack of active objects. So if your policy is processing objects which have other objects nested inside them, possibly a whole hierarchy of nested objects, then that stack allows you to keep track of where you are and kind of sort of go up and down a hierarchical tree. And there's also a recursion state property which is intended to basically say how you're going to do recursion. So a bit more about policy extensions. So the general idea is that this is something a bit along the lines of the TLM2 generic payload extensions. The extensions are indexed by the type of the extensions, and you can only have for a policy one of each type. And there are some methods which allow you to set and get those extension objects, find out whether a specific object type exists, to delete an extension, or to delete all of the extensions to a policy. And the idea behind these are that it allows the policy, its functionality, to actually be customized. And again, I'll attempt to show a few examples of how this might work. So there is a subtle difference to the way in which policies will be used in 1800.2. Previously, if you used one of the do methods to manipulate an object field, so for instance, do copy, do compare, if you implement those, or if you'd use the field macro to do those, then you would have ended up with some code which looks a bit like this code fragment here. So this is illustrating a do compare method where you're actually processing through all of the fields in an object in order to be able to do a comparison. So with 1800.2, this will still work, this approach. However, you could use extension objects within the policy to actually extend the way in which this comparison works. And again, I'll illustrate that later on. However, the do execute op callback can actually be used and is pulled in before the do method. And it can be used to actually process objects before you get to the do whatever method. So what we have is a situation, whereas in UVM 1.2 and all previous versions of the UVM, if you were calling compare, it would then go on to call do compare, which is either a hand-coded implementation or machine-coded implementation, or what goes on inside the do method has been populated by the field macros. And that was a hardwired system. Now what's happening is that when you call the do compare method, it will actually then call do execute op. And that will pull in UVM field op, which is populated for a particular operation. So for instance, it would be something like if you were doing printing, it would pull in a UVM field op to do with printing, containing the printer policy and containing any extensions within that printer policy. So that comes first, and it gives you an opportunity to do some additional work before you or have two versions of the field operation. Do execute op also has the option to set a flag to ignore the do method. So really it's sort of adding an extra function that you can call inline that gives you more flexibility over what's actually going to happen when you execute one of these field policies. So to put this all together, what's happening in UVM 1800.2 is that we've got more flexibility when it comes to working with policies. There's a way to change the behavior of the do whatever methods. There's a policy object operation which we'll now call do execute op. So you're able to add another layer of customization. So what it means is that, for instance, if you produce a sequence library or produce a library of objects, you can actually have the standard code in the do methods, and then the user can add in options which allow them to kind of just tweak the library to work in different ways. So I'll now try and illustrate this with a number of examples where this might potentially be useful. So the first one is a copier example. So I mentioned earlier that copy method now has a copier policy. So there's a slight difference in signature between 1800.2 and previous versions of UVM. But just going through this example, on the left-hand side, there's an example object. So you'll notice that this is a bus sequence item. I just took a generic bus type, and you'll notice that it's got read, an address, a read or write opcode, various things to do with cache operations, burst length, and so on. Now, what we have are two functions. One is do execute op, and the other one is do copy. So if you look at the top one on the right-hand side, this is the do execute op. So this is going to get called when the user calls a do copy method. So what you'll see is in that code, what happens is that it looks to see if in the policy there is actually an extension that exists. And if it does, then what happens is that you get a kind of filtered copy. So you don't copy all of the fields, you just copy some of the fields. And the other thing that happens is it disables the user hook, which is the do method. So just by adding the extension to the policy, we're able to sort of change the way in which the copy is working. And then if you look at the do copy method underneath, that's going across the whole set of fields. It's copying everything across. So this is just an example of how you might use an extension as a filter. And you could apply this to other types of policies, like compare, pack and unpack, and so on. So just a few notes about how copy is changing. First of all, it's now taking a UVM copier policy as an argument. So you shouldn't have to change any existing code because it's set up by default to accept a null. So that means that it should be backwards compatible with your existing code. Now, the other thing about the copier is it has a copy object method which is applied to the left-hand side when you get down inside it. So there is a recursion policy which by default is set to UVM deep. So what that means is that as you go down, you're making a deep copy of any objects which are embedded within your current object. And that will go down through the hierarchy of the objects. So that's something where you want to copy absolutely everything. UVM shallow is, as it says, it's a shallow copy. So instead of doing an absolutely deep thing, it's going through and just applying handles to handles. So that's one thing to know. And the other thing is that this policy object, unlike other policy objects like doPack, doesn't have methods for handling different types. It only has a copy object method within it. So the copier is actually retrieved during the execution of the copy method using getActive policy. There is, in fact, another recursion policy which is called UVM reference. And if you set that in a UVM copier, that will actually flag an error, because actually copying things by reference tends to break very quickly. So an error will be flagged if you do that. So that's the theory. I'm now going to try and show a few examples of how these different things might be pulled together. One possibility is if you're recording transactions in a simulation. Quite often, most of the time, you're interested in seeing those transactions maybe viewed in a waveform. But there may be times when actually all you need to know is that they've happened and that they were good. Maybe sometimes you just need to know a little bit of detail about what's happened. But there may be other times in the process where actually you need a lot more detail. This example is really just showing how you might filter field content within a transaction. It's like a verbosity setting, if you like, for transactions. So you would only record the detail that you need so that you can actually save on real estate in a GUI, and potentially it could have a performance impact. So in working with a similar sort of bus transaction type, and the first thing on the left-hand side is that we define an enum that says our transaction recordings are either going to be light, medium, or full. Then we have an extension, which is a bus recording extension, and that has some methods in it which basically allow us to set the recording level, and by default that's set to light. Then we have an API sequence that we put together. This is just for the purposes of the example. There are many other ways of doing this. What you do is, as the sequence is executing, it would get the recorder that the sequencer is currently working with. It would get the detail extension and then set it to the setting that you've set as an argument. So this is a way of being able to change the detail in the extension. And then in the sequence on the left, what's happening is that it's a higher level sequence that's actually calling two sequences which are doing data transfers in read and write directions, and also our set detail sequence. So as this executes, it starts off by setting the recording detail to medium, does a number of transfers, and then sets the recording detail to full, and then sort of finishes. So this is just sort of indicating how you might programmatically change the recording detail that's going on with various sequences. And again, there's many other ways in which you might do this. This is just an illustration. And then inside the doRecord method, what's going on, you'll notice, is that the recorder policy is coming in, and then we're checking to see whether the recorder policy has this recording detail extension. If it does, then we get hold of it, and we get hold of the level of detail. And then the rest of the code is about recording at the right level of detail. So by default, you always record the address, whether it's a read or a write transaction, and the response. The medium detail records a bit more information about what's going on. So that's things like burst length, burst type, and so on. And then the full detail would be all of the fields which are relevant to the bus transaction. So this sort of hopefully gives you a feel for how you might use this to achieve a kind of sort of filtering operation via these extensions. So the next example is one of a comparer. And again, I've probably stretched this a little, but again, it's really just to kind of sort of illustrate the sort of thing that you might be able to do. So quite often in a scoreboard, you might be comparing transactions of different types. So for instance, in this situation that I've put out here, you might have a system model that's generating generic payloads, and you might have a bus agent that's actually collecting bus-specific transfers, and what you're doing is kind of comparing a golden model against what's actually happening in your RTL DUT. So the idea here is that we are putting together a comparator that actually automatically does the comparison between a generic payload and our bus sequence item. So our comparator contains something which looks like this. So what we're doing is we've got an extension which we're going to add to the compare policy. And what this extension does is it actually compares our bus sequence item, which comes in on one side, against the generic payload which comes in on the other. And basically, as you look through this, you should be able to see that basically comparing like with like between the two types of transaction. But of course, the content and so on has to be reformatted because generic payloads works with an array of bytes, and our bus field may be, for instance, something like a 32-bit field. So that kind of manipulation is being taken care of within this policy extension. So this would be passed into a do execute op, and what would happen is that that compare would be pulled out as an extension object from the policy object, and its presence would signal to the do execute op that there is a way of being able to compare your bus sequence item against a generic payload. And so this is how this would work. And the other thing that you should notice at the bottom of the method is that the do method that would follow this is disabled, because the traditional do method would be doing comparisons between two bus objects. So the example scoreboard would be simplified as a result of this. And that scoreboard would declare the comparator, and it would embed that within the comparer policy. And it would pull in generic payloads, bus sequence items, and then in the actual run phase, what it would be doing is pulling in those transactions and just using the compare method directly in order to be able to compare generic payload against bus sequence items. Now, Mark Strickland touched on pack and unpack and some of the things that you are no longer able to do as you move from 1.2 to 1800.2. So it's important to realize what pack and unpack are really intended for. They're really intended to be able to move objects between one language and another, or another platform and another. So, for instance, there are packages around that actually move objects from System C to UVM, or from UVM to System C, by taking a transaction, converting it into a bit field, and then sending it across the language interface. Similar sort of thing happens with hardware transactors. So if you're working with an emulation system or an FPGA prototyping system, in order to get the transaction data to the BFM, you actually need to sort of change it from a system Verilog representation into a bitstream representation so you can actually transmit it over a hardware link. So the idea behind 1800.2 is it actually relaxes some of the restrictions that we had in earlier versions of the UVM. And the general idea is that pack and unpack should mirror each other. And in effect, if you look at the 1800.2 LRM, it basically says, however you implement the pack method, your unpack method should mirror that. So it's not applying any rules, and that's really being left as an implementation detail for the user. And what that means is that users are able to implement their own pack methods. Now, another area that there have been some fairly subtle changes to, but far-reaching, is in the area of printers. So in the printer classes, it's always been the case that there's been a UVM printer base class, a UVM tree printer, a UVM line printer, and a UVM table printer. And they all inherit from the UVM printer class. Obviously now, the UVM printer in turn inherits from UVM policy. As a user, you shouldn't notice any difference in that. However, there are two new classes that have been introduced, and again, this should be transparent to most people. The first is the UVM printer element, which is an extension from UVM object. And really what that's aimed at is capturing a line that would be printed on a printer. So it's an object aimed at storing line level information. And then there's another class that's been introduced, which is an extension of the UVM structure proxy, which is in effect a visitor object. So its purpose is to be able to go through a hierarchy of objects and collect printer element information as it goes through. So as an example of how, so the first thing to emphasize is this makes no difference if you're used to using existing UVM printers. But if you're looking at possibly putting together your own printer classes, one of the things that was always a bit of a problem was how you dealt with hierarchy and how you dealt with being able to manipulate hierarchy and keep track of where you were in terms of nesting and so on. And there's particular types of printer which could be useful in verification analysis situations. So one that I'm illustrating here is something called a JSON printer. So the idea is that as you look at a transaction stream, or maybe if you've got a complex test bench, something that actually prints the structure of the test bench in a JSON format. Other possibilities that might exist are things like XML files, CSV, and so on. So all of these things have description tags embedded within them that actually you need to reproduce, and those tags are actually nested within each other. So the UVM printer is now equipped with an element stack to enable you to deal with this hierarchy. So what we'll look at is an example of a JSON file that's looking at a transaction stream. So again, we've taken a sort of generic bus example. It has an extension object within it, just to illustrate how we might handle hierarchy. And you'll see that in the right-hand side, there is a doPrint method, which is using the normal doPrint type operations in order to kind of do things like print out the fields where there's an array of a burst type, actually print an array header. And at the bottom, you'll notice that there's a print object, which is designed to get hold of the information on the object. So this then ends up inside the JSON printer policy object, which is an extension of UVM printer. So it has things within it to interact with what's now the printer element stack. And in the UVM printers, there's always been an emit method, which is what's used to actually print out your code. So that emit element starts from the bottom element in the element stack, and that's actually a recursive call. So what it will then do is go through all of the elements which exist, and in the code segment on the right-hand side, you'll notice that we've got an emit element function, which is actually recursive. Because what happens is, as things are put onto the stack, they will be linked in with other objects. So what's happening is that you start off, you call print object, that actually pushes an element onto the stack. Then if you call print field, what happens is that the element is pushed onto the stack. It's then made a child of the parent, which is the object element, and then it's popped off the stack. And this process will continue for each field element. And then when there's an array header, what will happen is that will get pushed onto the stack, made a child of the parent object, and then it remains on the stack whilst other fields from that array are actually pushed onto the stack, and then it's popped off again at the end. And the same will happen for an object. So at the end of the doPrint method, you will actually end up with a stack that will probably only have one member, and all of the other elements will actually be linked into them. So you'll have a parent with multiple children. So if we go back to this call here, it says in the emit element, it's actually checking and calling this element proxy method to actually go off and find the children and actually print out everything that's happening. So what will happen in this printer is that it will go through and call, depending on what you're working with, either a single element line, or it will call down a recursive call to actually arrive at the children fields of all of the objects. And it will also be able to keep track of the indent. So if you're formatting one of these, for instance, JSON, in order to kind of make it readable, you need to indent it as you go. So actually you can keep track of what your indentation is as you go. So at the end, what we end up with is methods which are calling emitting a non-hierarchical element. That's what the first function call on the left-hand side is. There are others to do with opening up the hierarchy. So this is how you add a new element into the JSON file. And over on the right-hand side is an example of what might come out of this printer if you're recording a transaction string. And this is something that you could then write this to a file and then post-process this to understand what's been going on with your transaction string. You could also apply this to something like the component hierarchy, so that you keep a record of exactly what component hierarchies you've worked with.
I want to talk about 3 or 4 different dedicated elements. It's the abstract factory, it's about deferred initialization, and the last section is about dynamic UVM reg mapping. This should cover basically my section. Let's really jump into technical stuff. UVM factories. UVM factory, I mean, it's in UVM since 1.0, even I think even before OVM days. We know it for a long time. There's nothing really new stuff in there. It's almost the same API, nothing. The new thing which came with IEEE is the UVM abstract factory. That means that you can now register abstract types. Abstract types actually are virtual classes. And nothing has changed. In general, the only rule which applies is that when you invoke the creation, so when you try to invoke, create on that object, the virtual base type has to be overridden in the override chain. Very much like in System Verilog itself, right? So you cannot instantiate a virtual class, but you can inherit and you can make an instance of that. And that's very much the same thing as you can accomplish now in UVM. In order to tell UVM the difference is you use the old known macros, UVM object or component, utils, paramutils, or the begin version, and you bring in that additional abstract thing here. So you bring in that underscore abstract, and that's all you need to do. And if you had a standard version without the abstract before, you just replace that. And as a result, you can register virtual classes. So what does it bring to you? It's very much an alignment of what you can express in System Verilog and what you can express in UVM. So there is nothing that you need to make a decision, hey, should be a base class, but you cannot make it a virtual base class because then the object utils do not work anymore. So that is gone. You can make a choice and you can really align your System Verilog classes. If there are base classes in System Verilog, you make them base classes in UVM. You just need that change in the macros. As a side note, we enabled basically all classes in 1800.2 so that they derive from UVM object. They are factory enabled. That means you can override them. For some of the classes, unfortunately, it's not possible because the standard constructor takes a well-known signature. It's basically for the object, basically it takes a string, and for the component, a string and the parent. If the constructor has a different signature, unfortunately, we can't make it virtual with these standard factories. Now, let's take a look, make it real example. That's the typical example you had before. I didn't try to take fruits or whatever, or make it a packet or CPU. A fruit is not, I started with A and then, I said, that's not a good idea. So I choose animals here. So that's the typical thing. You start, you make a base class, and you try to compile, and you get a compile error, and typically you get a weird compile error because the actual error for the compiler is hidden behind the macro. It just tells you something with the signature of create doesn't work. So that's the typical pattern you see. So if you try to do that, you get an error, an abstract class cannot be instantiated. So the fix to take something away from that tutorial is very simple. You replace the object utils with the UVM object abstract utils, which only exists in the IEEE version. And then everything is good. However, and that's the one thing I said, that's the only rule which works. If you would invoke the create method before you do the override, then obviously it would fail because you're trading off basically a compile time error with a runtime error. So you would get a runtime error if you invoke the create before the override. You have to perform the override so that at runtime, the virtual type results through the override in a concrete type. And then the factory obviously can produce a concrete instance of basically a concrete type for you. Pretty straightforward. Second point by the factory is we did enable type aliases. Here a very small example of what happened in the past. So you have a base class deriving from UVM object, and you derive again a derived class from the base class, then you do a type def. So you make a type def and you essentially give the type name base another name. You just call it my very special A, whatever. And then you easily write a lot of factory things. So you set a type override, so you can set type overrides by names. So you can set override the type with the name base by the type with the name derived. Okay, that works since OVM days. You can also say that with the factory notion and refer to types. You can say my special A, my very special A, colon, colon, and so on. And you override this with derived get type. The reason for that is because the compiler knows that the two types are equivalent because you just do a type def. For the compiler, these two types are equivalent, so everything is good. However, what does not work is you cannot set a type override by name, and you cannot say override my very special A, because it's just a string, by a derived. Okay, that doesn't work because UVM doesn't know about that one. Okay. In short, a type alias basically allows you to do everything what the compiler knows about equivalent types, an alias for the type, to tell the factory the same information. So it allows you to use a different string type name for factory overrides other than the original type name. So how does that work? I just changed compared to the original example. We get the factory and we just declare that the two types, basically that my very special A is just the name for base colon colon get type. Okay? So we told the factory that the two things are equivalent. And then basically I can operate and say, here's a type override for my very special A and override this by derived. So at that point in time, the factory knows about that the types and the strings match, and then I can create overrides on these names. So I have made the factory basically knowing the same thing as the compiler does. Another use case, we do have a base class, and there's a tell me function in it, and there's a more complex derived class. I just derive from it, and then I use the command line processor to get my arguments from the command line. And what I want to express is, I want to set a type alias, basically something like complex colon int colon 5, to be an alias name for a parameterized type. Right? A parameterized type doesn't have a name in UVM. That's why you use the paramutils. However, I know that, and I would like to give that particular parameterization, I would like to give it a name, whatever that thing is, right? And I would like to give that from the command line. So what I declare here, I set a type alias that this complex colon int 5 is an alias, so it's a name for this particular parameterized type. And I give basically another name to that other complex type, and I just use basically a value and also change the one type, then I get the argument from the command line, and I can set a type override, right? And since I declared basically the alias, I can then set a type override, and I can create an instance easily. If you're not having that capability, you would end up in something like, if my type name equals complex int 5, then do this. If it's complex string foo, then it's that. So you end up in this typical big case statement, and if there's another type coming, you just add another one and another one and another one, and this gets longer and longer. So you do a lot of special casing. So that's one capability where you can really encapsulate things, and your code becomes much easier in the end. One thing to mention, all of the things here, it's not something you should, try the first day tomorrow morning. So your UVM still continues to work without applying all of that stuff here. But if you have a need for all of the things on the slides, then it's a good thing to remember what has been on the slides. Okay, so these are additional capabilities we're showing. Okay, next topic: UVM initialization flow. Pre-IEEE, the picture was there's system Verilog static initialization. If I say static initialization, that's all where you say something like in a class or in a module, you say some type, some instance name equals something. So you directly declare a type and initialize it in a non-procedural context. What happens there is basically that there are special phases in UVM where this automatically gets basically initialized before anything happens. And a lot of things here happen: initialization, UVM root setting, UVM factory, and so on. And knowing that, saying that happens up front, after that, your initial blocks happen. So static initialization happens first, then initial blocks come. And once you're on your initial block, you typically write something like you configure, and in the end, you just invoke UVM run test. And then UVM phasing starts, right? So that's the typical flow. Now, the important thing is to understand that there was a lot of UVM initialization happens, hidden actually in static initialization. That was working, that was okay. It was hidden in UVM utils, in all the object utils and so on. Most people were not aware that this actually happened, and they were just surprised that the factory works without doing anything, and everything was there. Why is that bad? It's called the initialization hell. There's no reliable order. So there's no reliable order of static initialization. A vendor could go and implement it this way or that way. Everything is compliant, but it's a different order. You may say, okay, it's okay, different order, I don't care. Where does it matter? If order is not specified, there's no way to be the first in line, or the second in line, or whatever. And it's actually then hard to be the first one and control things which come after you. It's pretty hard to control things like instantiate an own factory, an own UVM root, an own report server, an own transaction database, own policies from the very first beginning, right? Sometimes, especially when UVM is constructed, you want to control core elements of UVM. You want to override this. You want to override which factory is being used. And you can't do that once every type has been registered, because then only that already used factory knows about this one. But when you come with your factory, no way that this factory knows all of that. And something had to change here. Now, in IEEE, we do have a deferred initialization. Deferred initialization means we move initialization from static initialization all the way behind the initial block. Essentially, latest it happens at the beginning of run test. That means nothing is initializing UVM anymore. So if you start up your test bench and you come to initial begin and until you execute run test, UVM would not be initialized. UVM would just be sitting there, right? No factory loaded, no UVM root created, nothing, okay? Now, sometimes it is required that UVM is initialized. So you can still initialize UVM before. So initialization is either on demand. On demand means that when you need it, UVM is initialized for you. So if you invoke particular functions in UVM, like you're getting the core service or you're getting the root instance or stuff like that, that automatically triggers that UVM is initialized for you. There are additional capabilities that you can say, initialize UVM now. So if there's a need to, that you need to initialize exact at that point in time, you can explicitly invoke UVM in it. And obviously, if you're not doing anything like this, UVM is initialized automatically. So if you haven't initialized UVM already, then it's being initialized for you during run test. How does that look like? In the good case, and hopefully it's kind of the standard case, nothing changes for you. So you see, if you compare this to UVM 1.2 or UVM 1.1, there are no changes. You just see it in the comment that at the time when the display is executed, UVM root, UVM factory, and so on are not initialized yet. UVM is initialized only when run test happens. So no reason to be scared here. The second one, the on-demand initialization. So here I'm invoking UVM config db set, and under the hood, UVM is initialized for you. So once you execute UVM config db set, afterwards UVM is initialized. It was not initialized before, but it's initialized afterwards, and run test does not need to rerun initialization for you. Code-wise, you're not seeing a difference. Okay? Code-wise, it's the same code which was executed and was running before. And now the more interesting case. This is basically to illustrate how you reliably initialize UVM and provide an own core service. The core service is kind of a mini factory. The core service basically can return initial core UVM types, factory printers, UVM root. All of that is contained inside the core service. So what you can do is you can initialize UVM and you can provide an own mini service, an own core service. So you can easily create an own core service, the core service implementing the get factory method. And inside the get factory method, you return an instance of an own factory. Where does it make sense? And where you can use it? There are a couple of examples in the database, and you can create an own database like an own factory, and factory basically which logs you all the registration calls. You can have a factory which checks, which prints, which logs, which multi-stages. You can have multiple instances of a factory, all of that stuff. But you need to be able to control at what time you get a chance to override the factory. What else? If you're playing with UVM deferred init, there's also a new state of UVM introduced. So there's a state variable, an enum, and an accessor. And so you can query the UVM core state using this get core state. And the core, UVM core, is moving through different stages. It starts with UVM uninitialized, then goes through UVM init into initialized, then pre-run, running, post-run, finished. If there's an exception happening, so if a fatal or if the simulator explodes, then obviously you won't see that. If UVM knows that it's going to an end unexpectedly, then it's going through pre-abort and aborted. So you can query that state. And there's an even more interesting capability which has been added. It's the UVM run test callback. It's a callback to get a more reliable notification of beginning and ending of a test. So there's a beginning, there's a run test completion, and there's basically an abort, what you're getting. And what this allows you is to add your own actions into it, right? So you do not need to hook into the report catcher, or you need to disable that UVM does the finish for you. So you're getting reliable callbacks. And I just wanted to know this. This definitely is not a replacement for run failure detection. So there are a certain set of failures what that capability is unable to catch for you. So if you get an internal exception, this won't help you. This just gets you some information that some UVM is about to end in a good or bad state. This is an example, it's just a few lines. I'm using the UVM run test callback, and I just took into the pre-abort message, and I'm doing there, I'm executing a system command, and all I'm doing is basically I'm getting the log file of the simulator and passing that into mail and sending that to the current user. Okay, so if you're getting 1,000 runs failing, okay, you have a full mailbox. It should just illustrate the pattern, what you can do with it. Basically, doing something once a special condition happens. Writing that callback is pretty straightforward, and hooking it in, it's UVM run test callback at myCP. It's very, very much the same callback pattern. So not much to add here. Now let's move into UVM Reg. So one of the big things we started initially is to deal with some of the deficiencies in UVM Reg. Unfortunately, there's been quite some pushback and, small time, big wishes. And so basically we decided to leave the big changes out of UVM Reg in IEEE. However, what we brought in is a capability to deal with changing address maps and stuff like that. And in UVM and UVM 1.2 and before, you probably know that there's basically a log model operation, and that log model operation checks the address maps, sets up the addressing, and the untold stuff, it caches a lot of information. Caching is for performance. The rest, the check is good, but the caching is not really necessary for functionality. Unfortunately, log model could not be reversed. So once you log the model, only a limited set of operations were still possible. So you could change the address of something, but you could not structurally change your maps anymore. No way to change topology. All you can do is basically move up and down the maps. But that's it. And the problem is, you've probably seen that pattern, big interconnects, and they're changing all kinds of address maps at certain points in time, remap states, and what IPExact in addition gives you, it's way beyond of that what UVM Reg can do. However, in 1800.2, you're now allowed to unlock a locked model. So you can unlock and relock again. So basically unlock, do something, and lock again. So you can undo that thing. Users can unregister elements, so you can undo the add actions you did, add block, add register, and all of that. So you can unregister, undo that operation. The intent is that this works kind of a interrupt routine. So if there's a need to reconfigure your address map, you go into that interrupt routine and you unlock the model, you unregister all the things which is needed, or all the things needed. You regroup your address maps and you relog again, and you just continue. Basically, you switched addressing. You change the addressing topology at runtime, and then you can continue. That's not a solution or the brightest solution for all and everything, but it's a baseline capability which allows you to accomplish a lot of things. Right? We need to work more on that register stuff. That's a different topic. Now, let's make an example. We got two modes. We have a very simple thing operating in two modes, and it has two maps. One is register A and B, and then the second map is B and C, and in the other mode, basically, we just flip the registers. So in the old mode, you can just change the addressing where the registers are in that map, but you cannot, ungroup the map and then just reconstruct it. The idea here is you start in one mode, at some point in time you do a reconfiguration, you switch to mode B, then at some point later on you switch again back to mode A and so on. And the operation, obviously in zero time, right? While you reconfigure, you cannot operate your register model, right? Because it's not locked at that point in time. So you need to unlock, do your changes, relog again. You cannot operate it in between. Now, in that kind of zero time, you need to unlock. You can use all the unregisters, like you can unregister reg maps, reg blocks, reg itself, and you can create new registers, new maps. You can connect them up the way you want. And in the end, you just invoke log model, right? Very much like you do initially, you would do it, in this kind of exception. So how does a example unlock looks like? So let's assume we got that trigger, that reconfigure address map thing. And well, first of all, we unlock the model. Then we unregister. Unregister goes recursively, unregisters all that stuff. And then in mode A, we just regroup. We just do an add rec because the unregister, unwrapped all and everything. In mode A, we just set up the register, all the structure, put it into the maps, add the maps back into the top maps. So basically we rebuild the addressing hierarchy. In mode B, same game. Then we add the map to the top block and we lock again. Okay. So that way, basically, we can just ungroup all the registers and basically just rebuild the hierarchy again. Okay, there are a couple of miscellaneous notes. There are some changes to the register base classes. There have been some changes with respect to abstract or non-abstract. So there's a set of base classes have been non-virtual, but now became virtual. The main reason is there are certain classes which do not make sense without inheriting or without deriving first and doing an implementation. All of these classes are virtual now, okay? So if it's mandatory to inherit, then the thing is virtual. And there's a set of non-abstract based classes now, so they have been virtual, but we changed that to non-virtual, which is a UVM reg block. A UVM reg file, a UVM reg, right? So you can instantiate a UVM reg on its own without necessarily making the fields directly, and you can add fields from the outside. That's possible. Unfortunately, we discovered also one case where the LLM said, UVMM, for instance, as this thing needs to be abstract, but the implementation will be non-abstract because the LLM has a bug. Happens. And I think I already mentioned that. So all the classes in UVM which kind of match that base pattern, they are considered base classes and they should be virtual as such, right? And the side thing is we changed. Basically, there was an expression or a type, an enum type, and some literals matching kind of the path thing, and the path thing became renamed to door, right? So instead of UVM default path, it's UVM default door because it matches better front door, back door, and so on.
One of the things I want to talk to you guys about is making the simulations go a little bit faster. That's one of the things I want to cover in configuration. What we've done in the IEEE is to add a few additional capabilities to allow you to go and tweak your build time and make changes to your configuration in the beginning. And also I want to talk a little bit about callbacks and reporting. So the first thing I want to talk to you guys about is apply config settings. Apply config settings was a method that was not easily exposed to the users. And what this method used to do is it would find all the fields that were declared in your tickUVM field macros. And then it would do a resource DB lookup. Okay, this happened under the hood. So if you had a small test bench with a bunch of variables, you would notice that your build time took forever. Okay, so it can be a really big contributor. I've seen some test benches which had 75% contribution from this area. So one of the things that we've done is that there was basically no control over the build phase in UVM 1.2. You could not control it. If it was registered in the field macro, it would show up. Okay, so one of the things we've done is to give you a bet to turn it on and off. Okay, rather than have people do funky things. This apply config settings is a virtual method. Okay, and by default returns 1. If you turn it off, it goes to 0. Let's look at a fairly simple example. So what happens is that you've got a typical component, and what you can do is you can set up use automatic config and have it return a 0. And now what happens is that you can then, in your build phase, very specifically choose to pull things into the config DB. Let's say you had about 30 or 40 fields and maybe 3 or 4 arrays. Things can add up very quickly in the old way. Okay, I'll talk about how to speed it up further. But what you can see is that this use automatic config now gives you a way to customize which components actually pick up values from the config DB and which ones don't. Okay, so that is one area that you get. Using this judiciously, you can actually improve your build times. The second thing that I want to talk about is a rationalization of something called set local that Mark Strickland talked about. Basically, what we've done is to rationalize the various methods that interact with resources. Earlier, you had set int local, set string local, set object local. Okay, there are three methods. We've deprecated these. Okay, and then we've given you a single set local, which takes a UVM resource-based argument. Okay, and it's generic, so you can pretty much throw a type in it. You might wonder what this has to do with anything. Okay, and we'll go through an example that talks you through how you can use it. So you got a typical class myComponent, extending UVM component, and then what you'll notice is that I have an integer array here, okay, and then I also have written up this method called setLocal, which then looks for a certain thing, and then you can see that it looks at the name entire variable and then does a read. So you can do some amount of matching here. So you can also choose which fields are picked using setLocal. Now you remember I also talked about apply config settings in the previous slide. What happens is if you combine this with that, you get the opportunity to actually customize how your build phase actually looks with components. And this can have a fairly significant impact on your runtime in the build phase. Callback classes now extend from UVM callback and including UVM event callback, and UVM callback extends from UVM object. UVM callback extending from UVM object basically means it's factory enabled. You did not have that before. Okay. Event callback was its own thing. Now everything also extends from UVM callback, which by definition means factory enabled. Okay, we've added one additional method to UVM callbacks saying get all. What really has happened is that the LRM declares the function get all as having only the all callbacks part, as missing the input T obj. Okay. The problem is that you did that, you pretty much get everything. Okay, so I hope you see the difference. If when you're looking at a certain component, you want to get callbacks. The Accellera implementation is going to differ from the LRM in that one particular area. Let's go through an example. So talking about callback methods, okay, you can create a callback iterator that can go through the callbacks the old way in UVM 1.2. But there's a fundamental difference. What happens is that the iterator will only give you callbacks that are enabled. There was no way for you to get a list of all the callbacks that were disabled. That's what you'll see in the code. Instead, you can use the other method, which says get all, okay, which now gives you a list of all the type wide and the instance callbacks, and then check to see if the callback mode is enabled, and then choose to do something. Okay. Getting into event callbacks, there's been a slight change in the way event callbacks work. Event callbacks are no different from regular callbacks, and what you'll notice is that the older version of the callbacks had add callback and delete callback. These are now changed to a static accessor. Nothing new to alarm yourselves here. Okay. The only thing is the methods have changed. And now this is where I'm going to get your attention. A lot of people don't want to do a whole lot of extra work, but we have made some changes to the 1800.2, especially when it comes to reporting. Earlier, we had a bug in the library wherein the verbosity was actually UVM low for UVM report error. Okay. Now, with the the latest implementation, you may potentially see additional errors that you did not see with 1.2 before. Can I go over a few of those scenarios? Because what we've done is we've changed the verbosity setting. The verbosity setting is defaulted to UVM none for all errors. It was UVM low before. Okay. The errors and warnings were never filtered, only if you're using the verbosity. Here's an example. Here's the impact of the changes. If you used UVM report error with the default verbosity and with UVM none verbosity, you may have suppressed some errors. Okay. They will show up now. They will definitely show up, and these would be additional errors that were reported by your simulation that you will have to go deal with. If you used UVM report error with default verbosity and you had a catcher demoting it, it's possible that the catcher may not catch it, okay? Or it will show up, okay? Or if you used UVM report error with a specified verbosity other than UVM none, you might have potentially suppressed some errors. They're going to show up. So please don't blame us, okay? Please blame your simulation. One area of inconsistency that I want to talk to you about is UVM report warning still defaults to UVM medium, and UVM warning defaults to none. The library currently matches the standard that's presented today. Verbosity is ignored for warnings, and you can see it only if you are using a catcher. It's not often the case that catchers are deployed, but if there's a catcher, you'll only see it if you're demoting the warning. There's a tick UVM do macro. Some people love it, a lot of people hate it, but I'm going to stay out of that discussion for now. But there's only one macro in the LRM, okay? It comes with a bunch of default arguments, courtesy of system verilog. There's basically no additional functionality provided by the other do macros. So what we decided to do is we decided to save those 3 sheets of paper in the LRM and basically chop them out, okay? But, otherwise you were going to print, just imagine a 500-page document printed by 500 engineers. We've saved a few trees, okay? Okay, so the thing is that the functionality that was available with these macros is still available, okay? It's just available a slightly different way, which is what I'm going to go through. So for a clean API, redundant define should have been deprecated, but we've got a lot of people out there who are probably using these things because these things are from the days of OVM. So what we've done is we've placed the defines in their own file, and that file is included only when the deprecated flag is set. If you still love these macros, we're not getting in the middle, you may compile that file after the macro. Okay, you may compile that file.
We covered a lot of technical data. It may not have applied to everybody in the room, but we tried to cherry pick the biggest changes, the things that could have the most beneficial impact to you, or were most likely to trip you up on the conversion. So we wanted to show you that the library that we are releasing will always obey 1800.2, except for, as Uwe and Sri pointed out, there's a few times where 1800.2 actually gets something wrong. It is materially wrong. It's either, in the case of get all, just stupidly wrong, and we don't build in even a compatible mode for that. It's the way it's specified makes no sense whatsoever. So we put in the way that it was actually intended to be specified, and we open a bug against 1800.2. That said, those are very few and far between. Most of 1800.2 came from UVM 1.2, which had a few years under its belt, so there was certainly a level of stability to it. If you're coming from 1.2, your transition should not be all that painful. All right? We included that UVM enable deprecated API flag to make it even less painful. The most likely scenario where you would get tripped up by having that flag set or not set is if you are accessing a member variable inside of something like the printer knobs or the comparer, all right? The abstract field, all right? Those types of things are now hidden behind accessors. Now, you might say to yourself, oh my God, that's a software engineering practice. They just broke my code to make better software. Why would they do that? Turns out there's actually a reason for that. It allows the implementation to catch your changes. It allows it to increase its ability to provide you with useful debug information. If it's just a member variable, we don't know when you updated it. Right? We can't tell you when you updated it. We can't tell you why or how. If it's an accessor, we can catch that. And we've extended the library and added new hooks into the library so that not only can we catch it, but you can catch it. And that should make your lives easier. So that's why those types of changes went in. Again, all the stuff that was deprecated before 1.2, basically if you were running 1.2 with no special define set, all that old deprecated stuff, that is all gone. Moving forward, the committee is going to support basically deprecation on major revisions. So you have 1.2, that's a major revision. You have 1800.2, major revision. Things that were deprecated between the two, as much as possible, we are going to maintain. Anything that was deprecated prior is gone. In the future, and I'll cover this more in a moment, but in the future, if another major revision comes out of the IEEE, you can expect that all of the things that are flagged by UVM enabled deprecated API, they're going to be gone. And we'll have a whole new level of deprecation courtesy of the IEEE. But that is going to be the support model going forward. So why migrate to 1800.2? Well, for one, that deprecation model is going to mean that if you don't migrate, you'll get further and further behind the 8-ball. And if anything really important comes out, you're going to get tripped up by having to move forward in revisions. For two, all future development in Accellera is 1800.2. Now, we are a volunteer-led organization. We can only dedicate so much of our time. We certainly can't dedicate it to supporting umpteen versions of the library. We will only support 1800.2 moving forward. Now, there's a key item to note there with regards to deprecation. We are signing up to support those things that are covered by the enable deprecated flag. So if there's a bug in there, please report it. And assuming that it's compatible with 1800.2, we will fix that bug. So we are officially signing up for that, which is a stronger stance than we've made before when it comes to deprecation. That 1800.2 is absolutely paramount. Right? If there's a contradiction between deprecation and 1800.2, 1800.2 wins. But we will fix broken things that are in the deprecated code. The other reason to switch to 1800.2 is that now that we've added all of these hooks, implementations can do all sorts of nice things to assist you in your debug, to assist you in your performance, to simplify interactions for you. They can do that, and they don't necessarily have to completely override the library in order to do it. That was a big thing. I mean, if you look, I think all of the vendors have their own distribution of UVM 1.2 at this point. And if you were to do a diff between it and Accellera, you'd probably find something. There are quite a few user companies out there that probably have their own versions of the UVM library. And if you do a diff, there's a good reason for that. Moving forward, we won't need as many of those. Okay, I mean, vendors will still probably do it. They'll put in performance enhancements, hooks for their specific library, but users may not need to as much anymore because there are simply enough hooks in the library such that you don't need to rip into its mechanical bits and pieces there, all the black magic. You don't need to deep dive into that. You can just sit on the outside and work with it. But that only works if you're sitting on 1800.2. So all of that is a reason to move forward. So what do we ask of you moving forward? All right. First thing is, as soon as we release it, please try your code against 1800.2. By all means, turn on the deprecation flag. All right. I'd be shocked if your code just worked out of the box without the deprecation flag enabled. Like I said, there weren't major changes in there, but we put accessors in for everything, and those accessors are protected by the deprecation such that if you're using the old member variable and it's got an accessor now, that deprecation, you're broken. Any issues that you find, report them on the Accellera forum. If you have access to Mantis Hub, report them there. That's even better. But if you don't, and not everybody does, have access to Mantis Hub, put them on the forum. And that will allow us to track them. We have already signed up for, we're doing this early adopter release, and then we're going to be doing a full release that comes afterwards, somewhere in the Q3 window. And in between then and now, our primary focus is going to be on documentation. But that's because we're going under the assumption that everything we did is perfect. It works. Right? Every test we've got passed. So you guys are the source of the testing for any bugs moving forward after that early adopter release. Oh yeah, by the way, if it seems like we're taking too long, or if it seems like we're changing too much, and you want to change how something's working, please participate. All right? The UVM committee, if you're in Accellera, very easy to just request to join the committee. All right, we're all very nice, so please consider joining. What does the future of the committee look like? Near term, 1800.2 is what we're focusing on, specifically the 2017 release. Fun fact, the 2017 release of UVM in the LRM officially declares itself to be the 2016 release. That's in the standard. We have to do that in the implementation. Sorry, it's just a pet peeve. So we are implementing 1800.2. We're going to be documenting all of our changes. At some point in time in the future, IEEE is going to reconvene. And the primary focus, as of the last time the IEEE was together, the primary focus is going to be to fix the register model. Right? Uwe mentioned the fact that we made some changes, and I apologize, I say we and they when talking about the IEEE. If you take the working group members of the UVM working group and the working group members of the P1800.2 working group, there's like 2 outliers who are not in both groups. So generally, it's all the same. We all agreed the register model had a lot of work to do, but our choices were release the IEEE version and get it out for a 2017 release, even though we thought we were 2016, or release it for like 2020. I mean, registers needs a lot of work. So we know that we're going to be deep diving into that space again. In addition, the Accellera working group has the ability to add enhancements. So long as they're superset enhancements to the library, we can add them, and then we can get them into the official standard. All right. We already have, I want to say 20 of them queued up. They're all deferred until we get the official library out. But there are things that we all know could be better. And the only way to make them better is to say that they have to be better, and then somebody has to champion them. And that somebody could be you.